Okay, so good, what's that? Good morning, everyone. So let's see to start working. So the plan for today is the following. First, we have just a quick look to this screenshot, then we complete a little bit of theory, and then we do exercises on the topics we introduce this week. So about this screenshot, what do I want to tell you? Just a quick comment. So this is probably what we got from you taking the quiz, the online quiz I asked you to take before today. So the plan is next week to use, 10-15 minutes of each one of our lectures to go through the quiz. I will go and check the most difficult question, the question you found most difficult, and then we'll go through the grades, through the solutions during next week lectures, probably at the beginning of each lecture. So what we see here, okay, so I see there is a problem. So I forgot to, there is a problem with the microphone of some of you, so I muted. Okay, good. Now this should be okay. So you see this is what you will get in the final exam. Of course, then you can go up to 33 points, not only up to 15, like in this case, but the grading is the same. You got 10 questions, right? In the, 7 questions. In the quiz, you will get 14 in the exam. And what you see is that, for example, most people who took part at the peak in this region, so 6 points, so roughly half. So say this is the dangerous portion, because you can say that the grade you take today, you should double in the final exam. So if you get, say, more than 8, then you will get 16. If you get more than 9, then you will get 18. So if you are in this region and everything goes okay in the final exam, you can hopefully pass with probably 18 or probably 30 plus if you're in this area. But if you are here and you see there is a lot of people in this region or even lower, then you are in a situation in which probably you will have difficulties to go through the multiple choices. I'm not so worried about people in this area, because maybe these people took 2 minutes to go through the test. Maybe they just say, well, I want to see the question, and I don't bother give thoughtful answers. So probably this could be random answers. So this is why they are so low. This region is the one in which most of the people took the test are. This probably means you need a little bit more work, because 16, it will not take much to get to 18. And probably also these 2 areas with a little bit of work will be successful in the final exam. Okay, some of you ask, the difficulty of the question will be like today's quiz. I'm sorry, but it's very, very difficult from my point of view to answer that question, because, if you can answer them, you find them easy. If you cannot answer them, you find them difficult. What I can say is, yes, the level of difficulties is going to be this one, okay? And the time is relatively the same, meaning that you have 30 minutes for 7 questions. So it was a little bit less of what you will have in the exam. In the exam, you will have 75 minutes for twice the questions, so you have a little bit more time, but keep in mind that you will be also more stressed out. So more time, but more stress, you have to compensate the 2 things. Okay, sorry, this is not what I'm going to do. So now we go and speak a little bit about quadrics. This is more for your general culture. this topic is not going to be one in the exam, in the written exam. Okay, maybe we can speak about that in the oral exam if required, but not in the written exam. Ash Bairagi says there were no scientific computing questions. Yes, this is because I prepared it and I know exactly what to do of my part, and I wanted you to revise my part because I'm taking charge of that. Professor Painter will do the same for his part. Yeah. Okay, but then I cannot comment on his questions, so I think it's better if we share this kind of work. Okay, and I think the same question is from Beatrice Grassano. They will be similar level of difficulties. So for quadrics, the idea is that they are the three-dimensional, so the analog of conics, but now we are in R3. So they are surfaces. So surfaces in R3 defined by a degree 2 equation. So they look like a sheet of paper that is banded in 3 space. So this is the shape of a surface, the say not very good to make drawings person description of a surface. So it's just a blanket or a 2-dimensional object in 3 space. When I see the analog, is that this surface, which we will call Q, as a conic we call C, will have an equation of this kind. There will be some number variable square plus some other number variable square plus some other number other variable square, and then you will have all the product of the variables. So you will have y and z, and then you will have x and z, and then you will have x and y, and then there will be the part of degree 1, like for conics. So there will be some g multiplying x. It's a good idea to have a 2 here. Then 2h multiply y, and then 2i multiply z, and then there will be a known term, a number. And then everything is set equals 0. So you see, there is a quadratic part, like for conics. Then there is a linear part, again, like for conics. And then there is the coefficient, the constant term, j. And like for conics, we can describe these using matrices. So since this is a quadratic part, this is a quadratic form, which will be related to a 3x3 symmetric matrix. So 3x3 symmetric. And you can play with this matrix to decide which kind of quadric you will get. Someone asked, is this the last topic? No, it's not the last topic. We have still a little bit of time, and we will speak about other topics too. And then Ash Bairagi asked about paraboloid, hyperboloid, and so on. Yes, they are examples of quadrics. So in our short description, we only describe, not study, Q when G equal H equal I is equal 0. So basically, like we did for conic, we describe what are called central quadrics. So quadrics which have a center of symmetry, okay? So the only part you care about is the green one and the known term. And now we give a list of examples, and this is our description, okay? So for example, the first thing we can do, I go here, is to look at something of this shape. So say x squared over some number, y squared over some number, z squared over some number equal 1. Let's put in this situation. So you see, you only have the quadratic part. We kill the mixed terms because you can diagonalize the symmetric matrix and make the mixed term to disappear. So you only have this case to consider when there is no linear part. And for example, this is something you know very well. When A, B, and C are equal, Q has a very special name. Can you tell me what is Q in this case? It's a sphere, right? So it is the analog of a circle. We will say more about spheres next week, okay? Sphere. In general, Q is called an ellipsoid. Why do we have the name? The name comes from the fact that if you cut this surface with planes, you will get ellipses, okay? So a typical way of visualizing before computer existed, so to visualize Q, we cut it with planes. It is like a CAT scan, okay, in which you have a two-dimensional trace of a three-dimensional object, and then by these two-dimensional traces, you reconstruct the object. So what we do is we study basically Q intersect some plane pi, and we want to see what it is, okay? So just to give a very simple example, if I go here and I cut with planes pi z equals some number k, okay, basically what I do is remove variable z from the equation. So what is left when you study this intersection, I hope you see, is something of the shape x squared over a squared plus y squared over b squared equal 1 minus k squared over c squared. And this is an ellipse, right? And this is why you get the name ellipsoid. So when I cut the ellipsoid with planes which are parallel to the horizontal plane, what I will see is a collection of ellipses. One in the z equals 0 plane, and then one in, for example, another plane I can take, say, z equal 1. And since this number will get smaller as k gets larger, the ellipse you see will probably be smaller, till you reach a point in which this number is negative and there will be non-intersection, okay? So k large means that when you intersect, you get the empty set, okay? So, and this is true also if you cut with planes y equal k or x equal k. So basically our ellipsoid lives inside a box. And one way of describing it is the following. So you have this ellipse, and then you can try to give some three-dimensional flavor to it by drawing these lines, which are the intersection with the planes parallel to the coordinate plane. So the physical object which resembles the ellipsoid is a rugby ball, right? So it is just that. So this is a case you know very well. And when all these coefficients are equal, simply all these ellipses get to be circle, so that what you see is the sphere that you know very well. So this is the warming up example, okay? Now, let's try to make something a little bit more, say, mathematical. So use what we learn to study these surfaces. So I go here and say this is, we said, equal number, which in this description we'll call J. And you see that this part here is what we call a quadratic form. So it is x, y, z, x, y, z, multiplying a 3 by 3 symmetric matrix, which we can call matrix Q, okay? So this is the matrix having A, B, C on the diagonal, right? And then X, Z, X, Y is going to be here, so it's going to be there, and X, Z is going to be here, so this one is going to be there. And finally, we have Y, Z, so here it is, and here it is. Okay? So this is how this matrix looks like. And it is symmetric and real. So this means that with a change of coordinates, so this matrix Q will be P diagonal P transpose. And so we play the same old game in which from lowercase variable, we can pass to uppercase variables. And the matrix D as the eigenvalues on the diagonal. Right? And so the quadric in the new variables will have a nicer shape because it will be something like lambda 1, big X squared, lambda 2, big Y squared, lambda 3, big Z squared equal number J. Okay, so this is the canonical form as for the conics, canonical form. Okay, so what we can do with this canonical form? Well, we can make a list of possible quadrics as we did for conic, basing our description on this canonical form, which will work, as we said, for quadrics with a center, meaning no linear part, after changing coordinates. And this matrix P is describing a rotation in P3, in R3, rotation in R3. So it is as we did in the plane by in 3 space. As we said, we go a little bit faster here. We don't spend as much time as for the conics. This is not going to be part of the quiz. Is it good for you to know because of, for example, mathematical analysis number 2? So now we describe what kind of quadrics you can have. So, for example, if lambda 1, lambda 2, and lambda 3, and if we, well, this is minus J, right, which we call mu, as we did for conics. So if all these numbers have the same sign, what you get is the ellipsoid we just draw. If they have the same sign, you get the ellipsoid that we just draw, so the rugby ball. So something like this. And if lambda 1, lambda 2, and lambda 3 are equal, well, then you will get the well-known sphere. Okay, now what happens if the signs are not the same? So we say lambda 1, say lambda 2, and mu. same sign, and say that lambda 3 is opposite to the previous 3. Okay, so what kind of quadric do you get here? It's called hyperboloid. And it's called hyperboloid with one sheet. So this is the name. Now we make a sketch of what it looks like by using the slicing procedure we just saw. Okay, so we take an explicit example. So for example, x squared plus y squared minus z squared equal 1. This is the situation in which the first, lambda 1, lambda 2, and mu have the same sign, and lambda 3 have opposite sign. So, and we want to study this by cutting. So it's a good idea to say that x squared plus y squared is equal z squared plus 1. And so I will repeat the same game I performed before. So I will cut with planes of the kind z equal constant. Okay, now I ask you, for example, what do I see for z equals 0? So what is q intersect z equals 0? What kind of curve do you see? Remember, you just have to substitute here and see what you get. So what kind of curve do you get in the z equals 0? We get a circle. Yes, so this is a circle. So here we get a circle. Of course, it is perspective-like, so looks like an ellipse, but it is a circle, right? So, and then what happens, for example, if I cut with z equal 1? Well, now you probably know what it's going to be. It's going to be again a circle, right? So in this other plane, I will get a circle, but you see the radius here was 1. Now the radius is, well, square root of 1 plus 1. So it is larger. So I will get a larger circle. Okay, and this game will repeat. Oh, no. You will get a larger circle there. And actually, I hope you see, if you go with z equal minus 1, since you take the square, you will get again a circle of the same radius. Okay, and then you keep doing this. You get always circle of increasing radiuses as you go far away from the horizontal plane. So what is the picture that you will very often see of this hyperboloid with one sheet? Well, it will look like the cooling tower for some factories. It will look like the basket, the net of basketball. And people will usually draw it like this. So copy, paste, put it here. Perfect. And then you put some lines like this. Well, maybe we can make it a little bit more curvy. And you see, when you cut with horizontal planes, you will get circle because these lambda 1 and lambda 2 are also equal. In general, you will get ellipses. And it could be interesting to see what happens when you cut with planes containing the z-axis. Then you will get hyperbolas. Okay, this is why it's called hyperboloid, because when you cut with a plane containing the z-axis, what you will see is an hyperbola. You will see the two branches of an hyperbola. And this is why it's called hyperboloid. Again, this is just a sketch to let you know how the shape look like, and to let you know you can use this slicing method to study this quadric. Okay, then there is case 3, in which what will happen is that lambda 1, lambda 2, same sign, not mu this time, and then lambda 3, mu have the same sign. The quadric you will get in this case is again called hyperboloid, but it is hyperboloid with not one sheet but two sheets, which means is made of two pieces. Again, a good idea is to see an explicit example, so like x squared plus y squared minus z squared minus 1. So this is Q. So I can study x squared plus y squared equal 1 minus z squared. And if we perform the slicing technique we performed before, so what do you get for Q intersecting z equals 0? What do you get here? What do you think? When you cut with the horizontal plane, again, remember, it is substituting here or there. And so there is a minus 1 here, and there is a plus there. So what do you get? So let me write it in a more readable fashion, z squared minus 1. So what do you get when you cut? Well, imaginary circle, that's fine, Sophia Carnaug, which means is the empty set, since we are in R3 and we only care about real solutions. And you see, it will be empty whenever you cut with z equal t, t between 1 and minus 1, you will always get empty. Okay, so the first planes intersecting are the plane, for example, z equal 1 will intersect in just one point, okay? And then when you take the plane z equal 2, what will you get if you compute Q intersect with z equal 2? Well, you just put 2 there and you will get a circle of radius 1. And when you make this number to increase, you will get larger and larger circles. So when you make the plane go away from the horizontal plane, you will get larger and larger circle. And similarly happens downstairs, because again, if I take the plane z equal minus 1, I will get just a point, the intersection with the z-axis, and then I will get circles of increasing radiuses. And all of them will be joined together in giving me this paraboloid shape, which goes up and down. So again, the sketch that people usually do for the hyperboloid, not paraboloid, hyperboloid is something like this. You have two pieces. One is up, like a cereal bowl, but then there is the other part downstairs, facing you, but upside down. So this is the picture that you will usually, so let me try again. So this is the picture that you will usually get. Two cereal bowls facing each other, say. and this is the common, say, symmetry axis going through them, which in our case is the z-axis. Two sheets because there are two pieces, okay? Sheets simply means that is made of one piece or two pieces. So this is one piece, you see, is one object, the net of the basketball. Here you have two objects which are not touching. And historically, they are called sheets. This is the first sheet, this is the second sheet of the hyperboloid with two sheets. Okay? And then we have the last one, in which some zero will show up. So lambda 1, lambda 2, lambda 3, same sign. But mu is equal to 0. You can play with the equations if you want again, and this will be basically an ice cream cone, but double, okay? Two ice cream cones touching on the point, and this is called cone. Okay, so these are the fundamental types of quadrics having a center, and you see you have the rugby ball, the ellipsoid, then you have two hyperboloids when the signs are not the same of the eigenvalues, and then if the constant is 0, you get this cone, which is very easily visualized. Okay, we conclude with the last example I want to show you. So this is the last example, something like this, z equal xy. So this is not a central quadric. Because you see, it's not true that the linear part is missing. The linear part is there. And this is called paraboloid. So this is what is called paraboloid. And actually, you can also rewrite it in a nicer way by making a change of variables. So I just show you this kind of game once. So you can say, I multiply big X plus Y times big X minus Y, and I divide by 2. And if I do this, what you see is that you get something like x squared minus y squared. Okay, so this is the idea that people had to perform this. So they will say, well, we make a change of variables in which small x is 1/2 big X plus Y, and small y is 1/2 big X minus Y. This is just a trick to have a coordinate system in which the equation looks like the one we described previously, and you see that one of the eigenvalues is 0. So in our previous description, you see that lambda 1, lambda 2 are opposite, and lambda 3 is 0. And this is why it's called paraboloid, because like in the parabola, okay, like in the parabola, you get the description you wanted. Well, sorry, 1/2 is again here, and it is there to make, thank you, Sophia Kanauk. It was just a misprint on my side, and it is there to preserve orthogonality. That's the idea. Okay, paraboloid is what you will see in mathematical analysis, and this is actually called hyperbolic paraboloid, because you see that this part, when you put z equal constant, is going to be a hyperbola. So this is called hyperbolic paraboloid. So paraboloid because one of the eigenvalues is missing, sorry, is 0. And it is hyperbolic because these two are opposite, like in the hyperbola. And then you can draw it using the cutting procedure, in which you intersect Q with plane of the kind z equal t. So for example, for z equals 0, you will get just 2 lines, and then you will keep going on in this fashion. And this is the one which is a little bit tougher to visualize and draw, but it is not so bad. So it is like this. And sometimes it is called also saddle. So if you want some help visualizing it, my suggestion is to think of this as the saddle of a horse, in which all these portions here are parabolas. If you cut in this way, z equal constant, you get hyperbolas. And this is why it's also called saddle. That's, say, a nickname to remember the shape. This is the one which I want to point you out, because it is the new phenomenon you will see in mathematical analysis number 2. When you study extremal point, there are going to be points which are going to be called saddle point. For example, this point here, in which you see it is the top, the highest point if you go like this, but it is the lowest point if you go in this way. So it is not a maximum, it is not a minimum, it is the analog of a flex. Just keep this in mind. It is something that you will see in detail in mathematical analysis number 2. Okay, so this is the quick description we want to give of quadrics. So surfaces, just a taste of what you will be seeing in the future, a taste of what it can be done using matrices, quadratic forms, but in a larger number of variables. Okay, any doubt, question, or remark? Of course, now it is much, much easier to draw them using a computer than by hands. And then I'm looking in the chat, which I forgot for a while, sorry. So Arsh Bairagi says, can we say in one sheet parabola there is a common volume cover or they overlap? No, there is no volume because it's a surface. So it's just a sheet of paper which is just folded in 3 space. Sara Bordone has a question too. So from a cylinder, if we compress the surface, we get a hyperboloid on 1 sheet or a hyperboloid on 2 sheets. Well, no one of the two, because you see the cone is touching here, right? It's made by 2 pieces which touch. So it is basically 1 piece. But there is no hole. So I cannot go, it's not like a funnel. I cannot go from here to there because there is no gap here. So it's not this one because it is made of 2 different pieces. And it is not this one because here is empty inside that can go from top to bottom. If I put an object here, it will fall down there. In the cone, if you put an object here, it will just stop here because it is closed, okay? No water will go down. Okay. In the cone, someone asked, is it true that they have the same sign, opposite sign? Well, I understand what you mean, and you are perfectly correct. So it is, we want them not all of the same sign. So no one of them 0, but not all of the same sign. Because if you take the same sign, who was asking, there is Tiarmush, you get a complex cone. You don't get a real cone. So if you take them not all of the same sign, you get the picture we make. Thank you. Quadrics will not be part of the quiz. Pascal Viaki now, yeah, it was me writing not properly. Thank you for letting me know that. Okay, good. So now we can move to the exercise part, okay? So we move to the exercise part. So we have to cover 22 and 23, right? Well, probably 23 and 24. Okay, so a typical question is going to be about quadratic form. So is to study the character of definition. So character of definition of a quadratic form. Is going to be to decide what? Is it positive definite? Is it negative definite? Is it indefinite? Or is it semi-positive or semi-negative definite? Okay, so this is the task we want to accomplish when we are asked to describe the character of definition. Yes, the second time I see this question, no, we didn't finish the course because we still have 2 weeks to go. So there will be 2 more weeks of material. Last week we'll do revision, but there will be a full week of course material to go through, yeah, in which we do distances, spheres, and circles, okay? Okay, so this said, so let's see some simple example. So let's find the character of definition of the following, say, quadratic forms, and I give you one, say this one, say q x y, and then it is x squared plus 2y squared plus 4xy. Okay, so let's see how you can find the character of definition of this quadratic form. Okay, and remember, one way of doing that is to go through the eigenvalues. So I write for you the associated matrix. So it is 1, 2, 2, 2. And let's see what you can do with this. As soon as you have an idea, if it is positive, negative, definite, indefinite, or semi, you let me know. Okay, so we have a suggestion. Yeah, so one thing I want you to note is that, for example, Q of 1, 1. Can you tell me what is Q of 1, 1? What number do you get? Q of 1, 1. Oh, sorry. I probably, no, the matrix is wrote correctly. Thank you. It is number 7. So you see, since this number is greater or equal than 0, it means that Q is not negative definite, right? And there is also something smarter you can do, and probably you already saw. This number here is Q of 1, 0, and this number here is Q of 0, 1. So looking at the diagonal elements will tell you if it is, can help you to decide if it is not positive or not negative definite, okay? Then what you do is remember that the determinant is the product of the eigenvalues, which in this case it is 2 minus 4, so it is minus 2. So it means that lambda 1, lambda 2 are opposite. Since they are opposite, it means that A is indefinite, right? This was very simple. Since they are opposite, it is indefinite, okay? Any question, doubt, or remark? Okay. Just to make a comment, so people saying semi-negative, well, you must have eigenvalue 0 to have semi-negative, so the determinant must be 0, okay? So let's change the quadratic form a little bit, just by, I put it in red, making a 3 appearing here. What can you tell me about this one? So Paolo Lovera says, I don't understand why 2 minus 4. Well, because the determinant is 2 minus 4. What, maybe I'm not understanding your question, Paolo Lovera. Can you explain it a little bit better? Okay, okay. It's just the determinant of the matrix. It's very, very simple. For 2 by 2, it's very, very simple. So let's play the same game here. So I wait for you to tell me something, and then I will tell you something. What do you think? Is it positive, negative, positive, definite, negative, definite, indefinite, or... So Sofia Karnau says positive, definite. So let's have a look. This is 3, this is 2, and this is 2, and this is 2. I play the same game. The determinant, lambda 1 times lambda 2, is equal 6 minus 4. So it is 2. So it means that lambda 1 and lambda 2 have the same sign. Then it could be, so Q is either positive definite or negative definite, right? How do you decide? Well, I look at this number. So this is, we said Q of 1, 0 equal 3, larger than 0. So it is positive definite. It cannot be negative definite. Agree? So it's very simple. If you have Q of xy, you produce A, you look at the determinant of A. If it is negative, then Q is indefinite. If it is positive, then you look for A11 or A12. and you decide between positive definite or negative definite. So these will always work when they are 2 by 2. Very, very simple. So when you have only two variables, when the matrix is 2 by 2, everything is decided by the determinant and looking at the diagonal elements. Okay? Now let's see one which is not 2 by 2. Okay, let's see one which is maybe 3 by 3. So for example, let's see this one. Q of x, y, z equal x squared plus 2y squared plus 4xz. Okay, again, find the character of definition. So work on these and then you let me know what you get. Okay, so what do you think of this quadratic form? So we have a suggestion, well, an idea, but Ali Reza and Paolo Lovera, and now many of you, they had some ideas. So, of course, only one of you can be right. So let's see who is right. Okay, so let's go and do this together to learn what is the process. Okay, one way of doing this kind of exercises is trying to be smart, so not compute too much. Okay, so we look at the matrix associated to the quadratic form and let's write it down. So it is 1, 2, 0, 0. Then there is no z square. Then there is xz. So is a 2, and the 0 is a 0. Okay. So this is the matrix I see. There is no xy, but I have xz. There is no yz. Okay. So one idea is to say, well, I need the sign of the eigenvalues of A. So I don't need the eigenvalues. I just need the sign. So if you compute eigenvalues, it's fine, but maybe it is a lot of work, okay? It is not worth it, okay? So one thing I can do to start with is to say, well, the determinant is going to tell me the product of the eigenvalues. So why not I go and compute the determinant of this matrix. So 1, 0, 2, 0, 2, 0, 2, 0, 0. And it's probably a good idea to compute it with respect to this element. So it is 2, 1, 2, 2, 0. So we get minus, well, we get minus 4 times minus 8. Okay. So this means that the product of the three eigenvalues is not positive. So what can we say about this? Well, we can deduce that since this is negative and the matrix is 3 by 3, this implies lambda 1, lambda 2, lambda 3, not all of the same sign. And also, they are all not 0, but lambda I different from 0 for all I, right? They don't have all the same sign, but they are also non-zero. So what is the answer? Is indefinite. Okay, so hence A is indefinite. Okay, good. Now let's see another one. So Qxyz equal x plus y plus z square. And I ask you the same thing. Find the character of definition. Find the character of definition of this quadratic form. Paolo Vera has a question. Oh, sorry. That was too quick on my side. Thank you, thank you, thank you. I see what you're all correct. So I was too quick. So I can only say they don't have all the same sign. So it must be that, let me make a sketch. You're perfectly right. At least one is different from the other. So there is a positive and a negative, then could be something like this, or could be something like this, because I was a little bit stupid at this point. So let's do what we should have done. So, okay, this is something like this, or they are all negative. Yeah, thank you for letting me know. They can be all negative, of course, because there are three. Exactly, that was the point of having three. So the only thing you can exclude is not all positive. Not all positive. But they can be anything like in this shape. Thank you. Okay. Now we have these three options. The product is negative, so it means that there are at least two of different sign. Okay. What about this option here? They are all negative. Well, you look at the matrix, you look, for example, at this element here, you see that Q1, 0, 0 is equal 1. So it means that this is not possible, because it cannot be that it is negative definite. Okay, so the only two feasible options are either the first or the second, and they both lead to indefinite. So it cannot be that the eigenvalues are all positive because the determinant is negative. It cannot be that the eigenvalues are all negative because it is not negative definite. So it must be indefinite, and there is no 0. So now let me see in the chat. Paolo Vera, we'll come to what you ask in a second. He's asking, well, but what if the determinant is 0? Well, it is like in the case 2 by 2. If the determinant is 0, it means that either they are both 0, cannot be, or one is 0 and the other one is not. And so it will be semi-positive or negative definite, right? So, Paolo Lovera, this we'll see in a second, okay? Cesare Piemontese, I don't understand what is the point of this classification. What is the information useful for? Well, Cesare Piemontese, the information is useful for this reason. When you do function in two variables, and if you want to study extremal points, maximum, minimum, and the like, you need the character of definition of a quadratic form, which is called the Hessian matrix. So is the analog of the second derivative. So this is why you need the sign of the character of definition of a matrix is useful for mathematical analysis number 2. Okay. Then there is, yeah, but what you are saying, I'm just reading what you say in the chat. There are different options, but what we can say is that there are two of different. So what we are saying is that the number of negative must be odd. So if you don't want to put names here, what you are saying is that, so probably this is going to be clearer. So odd number of negative eigenvalues. So it's going to be either the first or the, well, now second line. Now you see what you mean. You have an odd number of negative eigenvalues, cannot be an even number. Now I see why you were perplexed, my fault, sorry. And about the odd number, it is either 1 or 3. 3 cannot be, so it is 1 negative, then there will be 2 positive, and now it's going to be indefinite. We'll see another method in the second, but this is what we could say in this situation. Being negative, we can say the determinant negative, we can say there is a odd number of negative eigenvalues, not important how you call them, right? So either 3 negative or only 1 negative and 2 positive. 3 negative cannot be because of Q11, Q in 1, 0, 0 being 1, and so it is indefinite. Now, let's have a look to this one. Okay, let's have a look to this one and see what you can do. Okay, Sophia Karnaut says semi-positive, and she is correct because you see Q of x, y, z is going to be greater or equal than 0 for all x, y, z in R, right? So it is semi-positive definite just by the fact that it is a square. Okay, so we don't need to compute the matrix. We can say it is semi-positive definite. And actually, it is not positive definite because Q of 1 minus 1, 0 is 0, right? So it is semi-positive definite. And if we want to be, we can also say is not positive definite. If you want to do this with the matrix, you need to compute more. But what I want to say is that often from the definition of the quadratic form, you can say what is the character of definition without requiring the use of the matrix. If you want to compute, well, here you get simply x squared, y squared, z squared, and then the double product, right? So the associated matrix looks like this: 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, and now this is the case in which we get a little bit in trouble because we know that the determinant, which is the product of the eigenvalues, is 0, right? So we can only say at least one eigenvalue is 0. So 1, 0 eigenvalue. But then it could be So 1 is 0, then could be both plus, 1 is 0, could be both minus, or 1 positive and 1 negative. And we need to decide which one is going to be. If you look at this one, again, you can say no because of Q100. Again, look at this diagonal element. It is positive, so it cannot be semi-negative definite. So it can only be either the first row or the last row. So only the two green one could happen and not the other. And now we can remember something about the trace of A, which is the sum of the eigenvalues. And now this is equal number 3, which means that only which is number 3, which again exclude this case here, because otherwise it would be negative. But again, this is not solving it, right? Because we know that 1 is negative, the sum is 3, well, but could be both positive or 1 positive big and 1 negative small and still get 3. So we need to do something more. When you need to do something more, sometimes you go and need and compute a characteristic polynomial, which in this case is equal to minus x cubed plus 3x squared. So it is x squared multiplying minus x plus 3. And so we see now that the eigenvalues are lambda 1 equal lambda 2 equal 0, lambda 3 equal 3. And now we can say, well, then it is semi-positive definite. So when the determinant is 0, you can go and have a look to the trace, right? Maybe it helps, maybe it does not help. If it is not helping, like in this case, because we were, say, unlucky, then you need to go and do the characteristic polynomial. Michele Porcus asked about the trace. Yes, it is the sum of the diagonal elements. And that is always equal to the sum of the eigenvalues. That's a useful fact, but is not giving you always the answer. What you see, however, is that the shape of the quadratic form gave you the answer almost immediately without computing a lot. But if you compute a lot, then you can get in trouble. Okay? Okay, final thing I want to remind you is this Descartes rule. Rule of sign, which works like this. So if P of x, some polynomial, a0 plus a1 x plus an xn, only has real roots, then the number of positive roots is the number of sign variation. What do we mean by sign variation? We mean that you write down a0, a1, an, and then you remove all 0 coefficients, so remove all zeros. And then you say that you have a sign variation if these have two consecutive ones have different sign. Okay, so Descartes' rule of sign tells me that if a polynomial has only real roots, then the number of positive roots is the number of sign variations. How do you compute the sign variation? You write down the coefficient of the polynomial, remove all the 0, and then you look at this string of number and you look to adjacent ones, if they have opposite sign, you say there is a sign variation, and so there is a positive root. For example, let's have a look at this polynomial here. Descartes Cartesian rest is the same thing. So let's have a look at the polynomial we have above. So P of x is minus x cubed plus 3x squared. So I write it 3x squared minus x cubed. So I only write the coefficient which are not zero. So 3 and minus 1. So are the non-zero coefficient. There is no known term, no degree 1 term. Now you look at here, you see there is one sign variation. Then implies one positive root. And note that this has only real roots because it is the characteristic polynomial of a symmetric real matrix, right? So let's make a note. Note, here it is. Asymmetric and real implies P of x only has real roots. That's always true, right? So I want to show you one more example. So let's say we have this quadratic form. Say q, x, y, z, x squared plus 2xy plus 4xz plus y squared minus twice yz minus z squared. And we want to study the character of definition. Okay, let's say we want to do this one. This we do together, and then the next one I leave you to do. So I write down the matrix. So I look at the square, 1, 1, minus 1. Then I look for the coefficient of xy, which is 2, I have it. Then I look for the coefficient of xz, it is 4, so I have it. And then I look for the coefficient of yz, which is minus 2, so I have it. So here is the matrix. And looking at the matrix, we see that I can take a positive number here, I can take a negative value there. So it means that it is not positive definite, it is not negative definite. So you see Q1, 0, 0 equal 1 means not negative definite. And Q of 0, 0, 1 equal minus 1 means not positive definite. So you see, just by looking at these two numbers, we can say quite a lot. But again, this is a lucky case. So it could be indefinite or semi-something, okay? Now, I compute a characteristic polynomial, and I get minus x cubed minus x squared plus 7x minus 9. I now write down the coefficients, minus 9, 7, minus 1, minus 1, and I look at the sign variation. So I have one sign variation, two sign variations, so two positive roots. Since x is not dividing, 0 is not a root, so it means that there is one negative. So 0, not a root. It means that the third root is negative, 1 negative. And so I can say that as we imagine, it is not positive definite, it is not negative definite, it's not semi, and so the matrix or the quadratic form is indefinite. Okay? This is an alternative way to the computation of the determinant. This is why how you can use Descartes' rules, Cartesian rule. But of course, the problem is that you need to compute the characteristic polynomial, and that can be not so nice to do. Okay, so we finish with one of these exercises, which I leave to you. So let's try this one. So Q, X, Y, Z equal X plus Y square plus Z square. Study the character of definition. Of this one, okay? So study the character of definition of this quadratic form. Francesca Zappula said we could have reached this result by studying the sign of the determinant. I'm just going a second backwards. If you study the sign of the determinant, in this case, you will get that it is negative. So if you then argue in a smart way, you say, well, the determinant is negative, then it is not the case that all the roots are positive. It means that there are either one negative and two positive, or three negative, right? And then you can say three negative they cannot be because of the diagonal one. And so, yes, you can do the same thing. This was just a way of using the Cartesian Descartes rule of sign. Okay, so Paolo Vera says, again, this is semi-positive definite because it is a sum of squares, right? For all X, Y, Z in R, thus semi-positive definite. And can I ask you, is it positive definite? What do you think? Is it positive definite? Okay. Why no? Can you explain why is not positive definite? Positive definite means takes value 0 only for X, Y, Z equals 0, right? So you say no, it is not positive definite, exactly because Q of 1 minus 1, 0 is going to be 0. If you go and compute this using the matrix will look like this. Hopefully no mistake on my side. If you compute the characteristic polynomial, it will be minus x cubed plus 3x squared minus 2x. So if you play with the Descartes rule of sign, you get minus 2, 3, minus 1. So you get 2 sign variation. So you get 2 positive eigenvalues. And P of 0 is 0. So 2 positive and 1 is 0. And so this is why it is semi-positive definite. Okay? Sophia Carnaut says, well, can we say that since the rank is 2, then the kernel is not 0, and so 0 is an eigenvalue? Yes, you can do that. Because having kernel 2, then the determinant is 0, and so 0 is an eigenvalue. Yeah, that's perfectly fine. That's perfectly fine. You can do that. Okay, so this is as far as we will go today. Any doubt, question, or remark? And as I don't remember who asked, remember, these will be very useful in mathematical analysis, physics, optimization. So quadratic form you need to know very well. Can you put the classroom note? Yes, I will do these today, exactly as soon as I'm finished with this. Okay, good. So have a nice weekend and see you next week. Bye.